The easiest way to explain concepts relating to motion is through a diagram. As in Feynman diagrams, the appearance of these diagrams tells us something about the nature of the situation. Here, we shall not call these pictures diagrams, as they are much more precise than that. We are going to discuss the graphs of motion. In each of the graphs, time is along the x-axis. This has nothing to do with it being an independent or dependent variable. There are no such things in this type of graph, really. It is because the graph makes most sense placing time along the bottom. We'll describe a situation for one set of y-axes, and then change this axis for another, more complicated one. Occasionally, we will flick back and forth between them, but time is always on the x-axis. Firstly, we will discuss displacement time. We will not expressly state the direction on this graph, as it isn't needed. In order to move from one place to another, you must use up time. So, as the displacement along the y-axis changes, there is a corresponding change in the time axis. The value on both axes are set and unchangeable. The scale will not change suddenly and throw off our thinking. The object we are recording is travelling at a steady pace. The value of the displacement increases as the value of time increases. We have a straight, diagonal line at an angle from the x-axis. Our object now sits still. It does not gain any more distance. How do we know that our object is stationary? Well, the distance has stopped moving, but the time keeps moving forwards. This is represented as a horizontal line on our displacement time graph. It is very important to note that our object is stationary. It has a value of displacement, but it is neither increasing nor decreasing. If the value of displacement were changing, then the object would be moving. Our object now decides to return back to where it started from. This is very tricky to describe accurately in a mathematical way. What do we mean by returns to the original position? On the graph it is obvious. The displacement returns to zero, as the object has reduced its displacement to nothing. However, if there were a distance time graph, this would not happen. In order for the object to return back to its origin, it needs to have travelled a certain distance. Whatever distance this object travelled outwards, it must now travel again. As direction is ignored, this is merely more distance. A displacement time graph would show this motion as an upward diagonal line, a horizontal line, and then a negatively sloped straight line. A distance time graph would show this same motion as a straight, positive sloping line, a flat, horizontal line, and then another straight, positive sloping line. Distance always increases with time. Displacement doesn't. You can think of distance as the person walking out a certain distance, stopping, turning around, then walking back again. The person has always moved forward because they have turned around. For displacement, you can imagine it as a person moving out to a point, staying still, and then walking backwards whilst facing the same direction to where they started. If this person then moves back beyond the point they started, then this is said to be negative displacement. The person is beyond the point where they started. This cannot happen for distance, as a person is always travelling forwards. They do not turn. They do turn. For displacement, the person moves both forwards and backwards. But what happens if this person changes speed?